lecture, we will discuss about Boolean algebra and logic gate. So every single digital circuit you will ever design, every processor, every chip you tape out comes down to just two numbers 0 and 1. So in this video, I'm breaking down Boolean algebra and logic gate from scratch. So binary operation performed by any digital circuit with the set of elements 0 and 1 are called the logical operations. So here any digital circuit works with the two states, right? 0 and 1. So when we perform the operation on 0 and 1, these are called logical operation. Okay. So now to actually design the circuit using these operations, we needed a way to represent them mathematically, like a symbolic language. So this is called Boolean algebra. The algebra used to symbolically represent the logic function is called Boolean algebra. Okay, so this invented by George Boole in 1854. Why does this matter to you as a design engineer? Because Boolean algebra is the tool we use to simplify logic circuits. Before you write a single line of a code, the logic you're describing is fundamentally Boolean logic. Okay, so that's why the Boolean logic is used to simplify the design of logic circuit. So Boolean logic ideas, these are classified into three ways: producing 0 1. So 0 is logic 0, 1 is logic 1. Unary operation, so this is first is transfer means whatever the value that has input, that will be transferred as output. Suppose it's 0, output is 0 also. This is complementary. So complementary means when whatever the value as in the input, that will be inverted, transferred to 1. It is 0 transferred to 1 and vice versa. And the third one is binary operation. So these are the actual design that we will use. Okay, so first one is AND logic, or logic, AND logic, or logic XOR. These are one of the most important logics in the digital electronics, and these inhibition and implication, these are mostly used in theory part. Okay, so here is one note. We know that if I have n numbers, so how many combination we can, how many combination are there to raise to power n, and how many functions, how many logical function are there to raise to power n. Okay, so here I have two numbers, n is 2. So how many logical functions are there to raise to power 2? 2 to the 4, that will be 2 raised to power 4, and that will be 16. Okay, so that's why if you see here, f0 to f15, these are 16 different functions I have. So let's look into this. So these are four combinations. Okay, 2 raised to power n, 2 raised to power n, 2 raised to power n equals to 2 power 2. These are binary, so these are four combinations. Okay, 0 0 0 1 1 0 1 1, and these are my 16 logical functions. So now this f0, so what is f0? This is null operation. So f1 is my AND operation, and f2 is, you can write this f2 as x y bar. So this is my inhibition operation. Inhibition. Okay, and f3 is, so if you see here, whatever the value of x is transferred to f3, so this is my buffer x. f4 is x bar y, so this is also inhibition operation. f5 is whatever the value of y is transferred to f5. So this is also a buffer that transfer y at output. So here f6 is, so if you see here, when inputs are same, output is 0, inputs are different, output is 1, so that is XOR operation. We'll discuss later. And this f7, so f7, if you see, whenever my any input is high, output is high, so that is or operation. And here f8 is, so f8 is the inversion of OR operation, so this is called NOR operation. And f9 is inversion of this f6 operation, that is called XNOR operation. XNOR operation. So f10 is whatever the value of y that is inverted and transferred. So this is y bar only. Okay, that is inversion of y. And f11 is x plus y bar. So this is my implication operation. Okay. And f12 is, if you see, this is my complement of x, means x bar. And f13, if you see f13 is my x bar plus y. So these two are implications. Okay. And f14 is NAND operation. Okay, this is the inversion of AND operation. Where is the AND? So if you invert these values, you will get NAND operation. And this f15 is identity operation, because for every combination output is high. This is my identity operation. So let's discuss about the symbols for the logic gate. So first is AND. So the logic symbol for AND is this. Okay, A, E, Y, output will be A dot B. Now for OR, symbol is this. Two inputs A, B and Y. Now the function will be A plus B. Now A and OR not. Not is represented as this. This bubble is there. The input is A, Y will be A bar. Now this is NAND gate. NAND gate is represented as this, the same symbol for AND, just a extra bubble is there at output. A, B, Y. So this is A dot B bar. Similarly for for NOR gate, this is same symbol is present, just a bubble is there. A, B, Y. Output will be A plus B whole bar. Now the XOR operation. For XOR, the symbol of gate is this. A, B, Y, A XOR B, A XOR B. Okay. And for XNOR, same symbol is there, just a extra bubble is present. Y, A, B, A XNOR B. Okay. and buffer is simply this, whatever the value at the input that is transferred to output a y is equals to a. Okay, these are the symbols for logic gates. Not and or are the basic logic gates, and or and not, these are the basic logic gates. Combinational logic gate are NAND, NOR, that is also called as universal logic gate, and XNOR and XOR are called arithmetic logic gate. Okay, so why it is called as universal logic gate? Because every single gate you can design using NAND and NOR. Okay, we can make any logic gate by using NAND and NOR. In the next video we will discuss about the conversion of every single gate using NAND and using NOR. If you found this video helpful, like the video, subscribe the channel and support the journey. See you in the next lecture. Thank you.